Okay, so we are discussing modern speech technologies and we discussed different things. We discussed about machine learning part, we discussed about classifier, feature extraction, so on and so forth. Uh, yes, this is our last class discussion. Now we are coming to speech recognition. We discussed yesterday that what are we detecting? If we are detecting words, then there are multiple words in a sentence. We can't map the whole sentence to one word, right? And how do we take care of this temporal alignment, this sequence? When I'm speaking so many words in a string or in a succession. How do I detect or classify these words in succession? And I don't even know the boundaries. I have to detect the boundaries and then classify the words. So, so basically, it is a sequence to sequence transformation problem, and we saw that how we can use something like hidden Markov models to do this sequence to sequence transformation. This is the typical ASR system, which is implemented in HTK toolkit, HTK toolkit from Cambridge, or from Kaldi toolkit, which is more recent and more popular one these days from John Hopkins University. So we discussed last time, what are we detecting? Are we detecting words? But we saw there are too many words. Then can we detect some smaller units like syllables, which are smaller in size? And then we saw there are still so many syllables. Then we further came down to phonemes, that we can detect phonemes instead, which are of manageable size. Like there are, how many? I think we saw 36 phonemes or something in Hindi language. So each phoneme is made up of, okay, we'll discuss this part. Today we are discussing something very practical. Today's topic is attributes of speech. So what are the different attributes of speech? So to understand this topic, first of all, we have to know, what does speech look like? So let's take up a tool, which is very standard tool, and I like it. It's called Prat. Prat is how many of you have heard of Prat? Just write on the chat window or speak out. How many of you have seen Prat? So yeah, Abhishek has seen it. Very good. Prat is a very popular tool used for audio analysis, and it is especially developed by uh, phoneticians or linguists who are working on speech from University of Amsterdam. So let's see what exactly it does. So first of all, let's start with recording some sound, right? New mono sound. Let me speak some sound, something. Can I speak? Okay, I will speak three words: Kamala, Kamal, Kamal, and Komal, right? They all are very similar, just small changes here and there. Let me record. Kamal. Oh, it seems it is not recording. Let's see. Save to list and close. View and edit. Yes, it recorded. Kamal. Yeah, it recorded the sound. Good. So let me record another one. Okay, let me rename it as Kamal. Now let me record another sound. Now this time Komal. Komal. Okay, let's see this sound. Komal. Komal. Oh, I think I started recording too late. Maybe I spoke too early. Let me re-record. I will delete this one. I will record again. Komal. I can actually rename it here itself. Komal. Save to list. Uh, I want to record new one. Now this time Kamal. Okay. Kamal. Kamal. Save to list and close. Okay, let's see. Kamal. Kamal. Okay. Now, mm, let's start with our first recording. View and edit. What is pitch? When I speak, you get a sense of shrillness. For example, I say, uh, versus I say, like all these sounds, they have different levels of shrillness. Even if I'm speaking the same sound, same sound, when I say Kamal, 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 like in music. So, what is changing in these three different sounds? We are perceiving some difference. What is that difference? That difference is the difference in pitch. We call that property, which is different in these three sounds, is pitch. What is pitch here? This is the pitch. Okay, I can go to this. I can say show pitch. It's already on. I can turn it off. You see the blue line has disappeared. This is, I can turn off the spectrogram also. Just pitch, show pitch. It is showing the pitch now. And what do you see here? At this particular point, the pitch is 116 hertz. If I click here, at this particular point, the pitch is 139 hertz, higher pitch, lower pitch. Let me record another sound, which is, let's say, a musical sound. New record mono sound. uh, okay, sorry, it was a bit musical, but what I'm singing is same sound in different pitch, different F naught or pitch. Save to list and close. Let us see what does it look like. You see the pitch. The pitch here is 127 hertz. Pitch here is 142 hertz. Pitch here is 162 hertz. So this property is pitch. In music, it's mostly about pitch. You change the pitch and you get different tunes or different melodies. Is this clear? Any question at this point? Please feel free to ask questions. So this property is called pitch. Now, why is this property important? Why is this property important? This property is important because this is the property which we are not interested in when we are doing speech recognition. Right? It means whether I speak Kamal or I speak Kamal or I speak Kamal, like all these different pitches, but I want my speech recognition device to give me the same output, Kamal. It should not, output should not change depending on my pitch, right? So this is a property which I want to ignore or I want to not consider in my speech analysis. Let us see what does it mean. Uh, to understand that, let us look at the next concept, which is spectrogram. Show spectrogram. What do you see in the spectrogram? Okay, now I can change the view range. See, the view range is only up till 1000 hertz. My pitch I can see from 70 hertz to 300 hertz, but my spectrum I can see from 70 hertz to 1000 hertz. I will change the limits. I go to spectrogram settings. I change it to, let's say, 5000 or 8000. What do you see? Okay, let me just go back. Show spectrogram settings. Let us also make it 300. Okay, what do you get now? Can you see something? All of you understand what is a spectrogram? Yes or no?
Yes, sir.
Okay, great. In case you don't remember, I will just remind you what is a spectrogram. Okay. So we say a spectrogram. So what is a spectrogram? You have your speech, right? So what you do is you take small, small windows with a constant hop size and constant window size. And for this each window, you compute the FFT, fast Fourier transform, and take the magnitude of it. So what you will get FFT will be something like this. You will get some peaks because it's a periodic signal. So you will get peaks in your FFT. One peak is at some F naught. Next peak will be at some 2 F naught. Third peak will be at some 3 F naught. In this way, you get peaks in your magnitude spectrum. This is the frequency axis and this is the X of F magnitude. Right? This is called spectrum. This is called now this is a vector. This is a vector, right? So you can put it horizontally like this and use color to specify the height or the magnitude. Color for magnitude. And this is your frequency axis. So basically you get a peak here. So that peak will translate here. This peak will come here. This peak will come here. Of course, on a gray level, on a gray scale, they will have different colors. Like this one will be more white than this, and this one will be the most white because it's the highest peak, looks like. So this is F naught, 2F naught, 3F naught. Right now, similarly, I do an analysis and I get a window from here. I put it next to this one. Here also I will get some peaks like this. Then I take the third window, put it next to this one. In this way, I will construct a matrix. So that is what is called a spectrogram. This is the spectrogram. So I'm watching the spectrogram from 70 hertz to 300 hertz. What do I get? This black portion was a peak, right? So in this case, white is the zero value, black is the highest value. This black is the peak. And what you see is this first peak is actually your pitch, F naught. The first peak in your spectrogram is actually your pitch, right? So now what I do is I will see a bigger spectrogram, let's say up to 8000 hertz. Okay. What do I get? I get the structure is almost similar. Okay. To make it more clear, let me make another recording. New recording.
Hello.
Ooh, ooh, oh. Right? Can you hear me, Avadhesh?
Yes, sir.
Okay.
Sir, I want to ask what is in the right, the frequency range, what is in the right and what is in the left? I mean, 70 to 300 hertz, and what is the range, the 0 to 8000 hertz? What it
Okay.
signifies?
Okay, good question. So this is basically for the pitch. This is the scale for pitch axis. Your pitch axis is 70 to 300, but your spectrogram is 70 hertz to 8000 hertz. I can turn off the pitch. This is just the spectrogram now from 70
Okay.
hertz to 8000 hertz, right?
Okay.
Now let us look at this sound. This is much more interesting. View and edit. Okay. What you see here? And this is also ooh. What do you see in this and this oo? So in this and this the first frequency has changed, F naught has changed, right? So you can see here, let me make it a bit smaller to 5000 hertz probably. So what you see here is your distance between the peaks has changed because the pitch has changed. The pitch here was how much? I don't remember. show pitch. The pitch here is 134 hertz. The pitch here is 167 hertz. But the overall structure looks very similar. But you compare it with oo sound, the overall structure looks so different, right? Here you have dark regions, here you have suddenly light regions. And the pitch has changed. This is so this both these oo sounds, you see the pattern, the structure, the color pattern is almost similar, but the distance between the peaks have changed. The distance between these peaks have changed. Like here it is multiples of 134. Here it is multiples of 189. Let me make another recording like this, because the E sound is more distinguishable. E, E, oo, oo. Okay, save to list and close. Let us look at this. This is renamed E, view and edit. Now you see there is a mistake in their pitch estimation algorithm, but let's ignore that. You know the pitch part you have already understood. I will remove this. Let's come to the spectrum part now. Take the full-fledged spectrum up to 8000 hertz. Now you see, this is A, this is E, this is oo. E, oo, oo. So you see, the A sound has a lot of weight in this region, whereas E sound has no weight in this region. Oo sound has got no weight in this region, but also this part is comparatively lighter. And again, there is some lightness here above, right? So what you see is, to distinguish between different vowels, the pitch is not useful. But what is useful is the overall structure, the shape of the envelope, right? If you go back to here, this envelope has a shape. The exact location of these peaks is not important, but the overall shape is important, right? That is why whatever features you studied, whether it is LPC coefficients or you studied MFCC features or you studied cepstral features, they are all trying to extract this overall envelope. So they are trying to ignore the individual peaks or individual partials. These peaks are called partials also. Ignore these individual peaks and just focus on the overall envelope, because that is what is useful for distinguishing different vowels. Is this point clear? Is this point clear?
Yes, sir.
Yes, sir.
Great. Okay, now I will show you something.
Sir, could you explain about wideband spectrogram? This is narrowband, right, sir?
This is a wideband spectrogram. What is a wideband spectrogram? Okay. When your window is, I'm sorry, I made a mistake. When your window is large, you get a narrowband spectrogram. Am I correct?
Yes, sir.
Yeah. So this is a narrowband spectrogram. Let me go to the spectrogram settings. Here I can change the window length. This window length is 0.1 second. If I make it 0.02 second, that is a standard. This is the standard window length used for speech analysis. Let us see this. Now what you see, your how do I show you? Okay, let me make it. Now your pitch information will be much ignored. Let me go to 300 or 500. You see, you cannot find out your pitch very accurately now, right? Because your peaks are all merged into each other. Your partials are all merged into each other because your window was very small. But now, if you look at the overall picture, you get much better envelope, right? You see your envelope here. Here it is a white regions. Here, these are white regions, and here again, white regions. These regions have lower energy, like that. You can very easily see. The formants, sorry, and the envelope is very easily seen in the with a smaller window, right? Sorry. Is that clear?
Sir, so here what is usually analyzed?
Pardon?
Where is wideband generally used?
Okay. So you use a wideband spectrogram or a narrow window spectrogram if you want to ignore the pitch information and you just are interested in the overall shape of the envelope, which means for speech recognition, for distinguishing different vowels. It's very common, no? Means you don't have to memorize anything. Just you see, you don't want individual peaks, you want the overall structure. So what will you use? So if you don't want individual peaks, you want the overall structure. So you make your window small, because when your time window becomes small, your peaks become more hazy, right? Do you get it, Jayant?
Yes, sir. Yes.
Okay. So this is the thing. We have got this peak structure. Excuse me, just excuse me for a second. Yeah. So it's very simple, right? You want to get very precise estimate of your pitch, then you will take a longer window. If you don't want your pitch information, you want just shape of the envelope, then you take a smaller window. That's it. And for ASR, you do want a spectrum only, not the pitch. So that is why you take a narrow window. And I mean, the time window is small, so a wide band spectrogram. Okay. Okay, so this is what now we are interested only in the spectral envelope to distinguish between different sounds. Actually, to let you know, there are many people who are experienced and they can just look at your spectrogram and they can tell what you are speaking. Can you imagine? They will just construct a spectrogram using Pratt and they will read the spectrogram and they will tell you what you are actually speaking in this recording. So they will say, oh, this is an sound, this is an E sound, this is an oo sound. They are called spectrogram readers. They're very expert. Okay, but it's not difficult if you understand that what they are actually looking for. Okay, let's come back to our, okay, now let the next concept which I want to discuss is formants. So what are formants? Formants are the peaks in your spectral envelope. Now, not the peaks in spectrum, but the peaks in spectral envelope. They are called formants. So I will just plot formants here. I hope it will do a good job. Oh, it's taking some time. I didn't do a very good job actually. It didn't do. Maybe some settings have to be changed. Oh, number of formants is one. I have made a mistake here. Number of formants, let's say we take 5 formants up to 3000 hertz. Window length is 0.025. Okay. Nah, didn't do very good job. Formants, format settings. No, how come it became 15? I did 5. Yes, yes. This did a good job. Now you see what is a formant. For the sound, you see the formants are very consistent. Means the peaks in your spectrogram or the peaks in your spectral envelope, they are very consistent. You see, first formant is here, second formant is here, third formant is here. And similarly, this is again an sound. First formant, second formant, third formant. These are some mistakes actually. If I change it to, let's say, only 3 formants. Every algorithm has its own mistakes, right? So, okay, this is much better picture now. See the first two formats, then third format. There is a long gap between here. First two formats, third form, but they are very consistent across different utterances of the same vowel. Now look at this. This is E sound. First format, second format is very far. Right? This frequency is how much? 2000, about uh, 2250, 2250 about, right? This is the second format, and first format was 300 something. But for the sound, first format is about 600, then 1200 something, and then 2700 something. So clearly, by just if I tell you the values of formants, you can tell the distinction between different vowels. Am I understandable? Is it clear? Is it clear?
Yes, sir.
Yes, sir.
Okay. So these are called formants. So when you do your LPC analysis, they are actually trying to find out the formants. LPC is kind of, you're trying to find what is the envelope of my spectrum. So if you remember the source filter model, what was the source filter model? So from the source filter model perspective, do you remember source filter model?
Impulse train generator and random noise generator.
Yeah. What happens is you have got, I'm plotting the spectrogram only, X of F. This is glottal pulses, right? These are just peaks of same height or something. F naught, 2F naught, 3F naught. Actually, it goes much higher, like it could be. Now, what do you, the source filter model of modeling is there is a filter. It could be vocal cavity, the oral tract, everything. And it induces a transfer function H of F, whose magnitude looks like this, something like, let us say if this is an E sound, something like this, right? This is for E sound, right? The first format is close to about 300 something. Second format is very far, 2500 something. Then what you get in the output is, of course, this structure will be maintained, the envelope, and then there are peaks like this. Right? Ultimately, you get this, right? So your LPC analysis is trying to find out the peaks in your HF. Means it's one way to see things. So basically, your vowel information is there in your H of F, not in your glottal pulses. Glottal pulses contain the pitch information. The filter or the H of F contains your formants, the peaks of your spectrogram or the shape of the spectral envelope. The peaks in your spectral envelope or the shape of your spectral envelope. Similar, so same thing is done by MFCC features also. In MFCC features, you first compute the spectrum, right? And then you compute the magnitude spectrum, which is okay, this thing. And then you do a DCT, discrete cosine transformation, in which you consider only the low frequency components. Low frequency components are essentially these envelope things, right? As you go to higher frequencies, you will be capturing the individual peaks, but the low frequency will be the overall shape. That's why you take the top 13 or something low frequency components of your DCT, and that is the same is the concept with Capstrum. Capstrum is also same thing. It is trying to capture the overall shape, like DFT of DFT. You have the DFT, take its magnitude, again a DFT will give you this spectral shape. So this is the origin of all the features which you have studied in your first half, whether it is LPC features, MFCC features, Capstral features, whatever. Just you're trying to capture the shape of the envelope. And why are you trying to capture shape of envelope? Because that is what carries the information about which vowel it is. Is that clear? Is that clear?
Yes, sir.
Yes, sir.
Yeah. Now you can design your own features because you know what exactly you are looking for. Okay, let's come back to our presentation now. Attributes of speech. We saw what is pitch. So the utility of knowing this is we use smaller windows or wideband spectrum to disregard the pitch information so that we can only focus on the spectral envelope and not on the individual peaks. Now coming to spectrogram. What is spectrogram? It has got some structure, it has got peaks, etc. And we just discussed. Then formants. Formants are the peaks in the envelope. So we are interested in using spectral envelope to ignore the individual peaks or partials. Partials are the individual peaks. Now let's come to discuss another important thing, which is called co-articulation. So until here, everything is clear. Do you have any questions until this point? What are formants? Because to understand co-articulations, you have to understand those things first. Any questions? Any questions at this point? No? Good. Okay, let's now dive into next topic, which is co-articulations. What are co-articulations? So let's go back to our recordings. I will see. We turn off the formats. Let us look at two sounds, Kamal and Komal. Right? Now what you find here, the same k sound. Look at this k. K. It looks like this. Now, when it becomes ko, it looks very different. The same sound ka, so the ka phoneme, it changes its appearance or its spectral properties when it is coming with a versus when it is coming with o. You see, it becomes komal, o, but this similarly here, kamal. This is a. You can now see, now examine the properties of this second a. Ka, ma, a, la, ko, ma, a, la. So it's both have a, but see here the a is all flat, right? But here the a glides into an a, right? It starts from o looking sound and then becomes an a. So because of co-articulation, there is a transition from one kind of spectrum to another kind of spectrum. And because of that, if this is too short, then this may look very different, right? And even now you can see this transition is bringing in so many changes in the spectrum, right? So this is a clear-cut change that how a sound changes when a comes versus when o comes, right? This is called co-articulation. When things are articulated together, then we have our physical limitations, right? Our mouth does not move at infinite speed to change its positions, but it is changing slowly, slowly. And because of that running speech, co-articulation, those changes, they induce different kinds of spectra. So these two spectra, they look very similar, but in the beginning, you can see there is a lot of change. Similarly, if you go to look at the sound of k, let me do, I have out. This is k sound. This is also k sound. This k and this k, the spectra look little similar in the beginning, but then suddenly it becomes very different because of co-articulation effect. So basically it means that when two different sounds come together, both of them, they change a bit because of co-articulation, because of association of the other sound, you can say, right? That is the phenomenon of co-articulation. This means if I am detecting an if I'm detecting an a here versus I'm detecting an a here, simply detecting an will not work all the time, right? Then what will be this sound, this portion? If you are classifying this portion as an sound, what will be this sound, this portion, right? So so that is why you do not detect or classify phonemes, but you split a phoneme into three parts: the beginning of the phoneme, middle of the phoneme, and the end of the phoneme. To understand, you can say these are the parts, but statistically they are decided by the HMM model. Statistically, it finds out what are those regions which are common. So whenever an O when an O comes before an versus when an comes before an the beginning portion of the second will be different in both the cases. That is why we use the concept of triphones. Instead of detecting phonemes or classifying phonemes, we detect or classify triphones. Basically, you split one phoneme into different categories depending on what was preceding and what is succeeding it. Okay, let me give you an example for this. Actually, I think it's good to give an example here. Mm, Continuing from our O example, um, let's say this is a silence or a blank followed by k followed by o. You can say silence followed by k followed by a versus silence followed by k followed by a. So both these, so I will not model a k. Instead of a k, I will model silence followed by k followed by o. Right? So if you remember our analysis last time, so the building blocks of our speech, we thought phonemes can be used, but it is found that instead of using phonemes, if we use triphones, basically clusters of phonemes, clusters of three phonemes, then it becomes, or you can say triphonemes actually. Triphonemes. It's in literature, it is popularly called as triphones. You can call it as triphones or triphonemes. So these triphones are basically our basic building blocks. So how many triphones will you get if there are 38 phonemes? If there are 38 phonemes, how many triphones will you get?
12,
Pardon?
12,
How 12?
3, 3, 3.
Sir, can there be any combination?
Um, yeah, to calculate these values, you can say any combination, but later you can put some constraints that, okay, k cannot be followed by kh, for example, right? How can you say ka kha? Or maybe yes,
It can.
In Hindi it can occur. Yeah, in Hindi it can occur. Like in some akhar, akhar. I don't know. Yeah, yeah, in Hindi it can occur. Yes. So yeah, so later you can put some constraints, but okay, theoretically,
39p3.
38 C3, like this.
39p3.
39 P3.
P3.
Yeah. Mm, but there could be repetitions also, like ka, like you have a word where double ka comes in Hindi, makkad, something like that, makkad. So in makkad you will have ma plus a plus ka plus ka plus da makkad, makkada, makdi. Oh, makdi is also a good word. No, but makdi does not have double ka. Makkad has double ka. Or makkar has double ka. Oh, sorry, there was an a before. Makkar, makkad. This is makkad, where we have double ka. So your triphone will also have double ka. So okay, means in general it could be 39 to the power 3, something of that order, right? Of the order of 39 to the power 3, 30, yeah, because there is silence also. 39 to the power 3 of that order, right? Okay, so this was all about our co-articulation thing, and that's why we get triphones. Now let's come back to zoom out and look at our original model. So we have input speech, we put it into a deep neural network, and we get these triphones. Instead of saying probability of phonemes, now we are saying probability of uh, these triphones. Okay, and then uh, okay, okay, I think we will discuss that point later. Okay, now we have to string together these triphones. So we call it as, we do it using HMMs, and then we use, okay, let's discuss one by one. First of all, input speech acoustics. So this you have already seen that you have a speech waveform, you do time frame analysis, you extract some acoustic features, and you know that these features are such that they capture the spectral envelope of your speech. Now you go to your DNN part. What does it do? So you can use here Gaussian mixture models or DNNs, whatever you like, to basically estimate probability of the state given the X. This state could be anything. It could be phonemes, triphones, whatever you like, right? So ultimately you want to get probability of different states given the X. Then you are using HMMs. In the HMMs, you are stringing together these words. You string them together, and you say, because output of this is just probabilities. You don't know what is the best path which maximizes those probabilities. So you put a constraint that, let's say if the word is one, then after ver I will get a only, and then na. It cannot happen that I get ver, then na, then a, right? Even if the best path may be something like that, but I know that that is not a valid word which I'm looking for. Then one is a valid word, so that word will get the maximum probability with this constraint, and that's what your HMM will uh, give out this path. And then there is a lexicon or FST which says, okay, let us say I am detecting three words, 1, 2, and 3. Whenever you see ver followed by an a followed by a na, then you say I saw a 1. Whenever you have a t followed by an u, you say I saw a 2. Whenever you say see a th followed by a r followed by an e, you say I saw a 3. So, and then you end at this state. So it's called a finite state transducer. So what does it do? It says, when if I see this sequence, then this means I saw 1. If I saw this path or this sequence, then I saw 2, means the output will be 2. And if I saw this sequence, then my output will be 3. This mathematical model is called a finite state transducer. In this way, finally we arrive at the word. And so basically you saw we are stringing together things where we only know the probabilities of these things at different times, right? We string together ver, a, na to get 1, and the lexicon will tell you what are the valid words, like what are the valid sequences which you can string together. You cannot string together a woo, right? Because woo is not a word in our dictionary. And even if your model says I detected a woo, you will say keep quiet. You are doing something wrong. Let's recalculate. So it will say no. Okay, maybe if not woo, then little less probabilities of 1. So you say okay, take 1 as a possible option. Okay, then we have a grammar. So people don't speak. I will never say. Um, for example, I have to say I am. I will never say I is, right? Because in grammar, in English grammar, I is not allowed. और मैं अब मुझे for example in Hindi I will have to say मैं खाता हूँ. I will never say मैं खाते हूँ, because खाते will not come after मैं, right? There are many grammatical constraints in your speech recognition or in your final speech, whatever is the output. So you put those constraints using these finite state transducers. You say that I can see after मैं khata can come, but khate can never come. मैं खाते हैं. Nobody will say like this, right? So that is what these constraints you put so that your output sentence is much more meaningful. So this is what is, I think we will discuss these concepts a little later when we discuss the mathematics of it. But today's class, the focus was to give you an overview that how things are moving. Now,
Sir,
pardon?
sir, I have a doubt in the previous. When we make FSTs to decode each word, so should we make FSTs for each word?
We can make FSTs for anything. We can make FSTs for individual phonemes, for words, for sentences, anything. It just means whenever I see this sequence, this is the output. Whenever I see the sequence of these phonemes, this word is the output. Whenever I see sequence of these words, this sentence is the output.
Sir, so for each possible state, we have to make one FST.
FSTs are more general. Basically, they help you to encode your constraints, and they are very much flexible in that sense. Just a minute. Give me a second.